Hello everyone, this is Miss Maneely, and I am going to go through the Algebra 2 quarterly or quarter 1 assessment review packet. I'm going to do this in 3 videos. So this first video we will review systems of equations in 3 variables. In the second review or the second tutorial I'll review quadratic functions, and then in the third I will review polynomial functions. So let's get started with the first problem on your review packet that deals with classifying systems as either inconsistent, consistent independent, or consistent dependent. One of the things that I was finding with my students is they were getting confused with labeling the solution versus classifying the system. So if you think about a system of equations, whether you're dealing with 2 variables or 3 variables, there are 3 different types of situations you can end up with. You can end up with a situation where there is one solution. You can end up with a situation where there are infinitely many solutions, or you may end up with a situation where there is no solution. And so what that looks like graphically, if there's one solution, that means there is one point of intersection. And so if you're dealing with 2 lines, that would look like 2 lines intersecting, right there. If you're dealing with planes, and that's basically what you're dealing with when you have equations that have 3 variables, it would be like if you think about 2 walls in a room and then the floor. They all intersect in the corner. So that means that there is one solution, it's one point. If there are infinite solutions, that means that there are infinite points of intersection. And so those infinite points could be on a line. So for example, if you're dealing with a system of 2 lines, it could be that the 2 lines are the same. Or maybe you're dealing with planes and all 3 planes are the same. They're all on the same, they all overlap each other. It could be that if you're dealing with planes, you've got a situation, I don't know if I'm going to draw this very well, where they all intersect. It's not looking very good. Where they all intersect on the same plane or on the same line. I'll show you on the other page. I'm just not very good at drawing this. But it would basically be where all 3 of your planes intersect at a line. So infinite solutions basically means infinite points, or the solution is a line or a plane. All of those cases would indicate infinitely many solutions. And no solution means that there are no points of intersection, or no points in common. And so if you're dealing with lines, it could be that you have 2 parallel lines. It could be that you have 3 parallel planes. It could mean that 2 of your planes intersect, or they all intersect, but maybe not at the same place. So think of like a triangle, where like each one of the sides of the triangle is a plane. So they all intersect with each other, but just not in the same place. That would be another example of a system with no solution. So when we're talking about labeling the solutions in terms of the number of solutions, we'd say there's either one solution, infinitely many solutions, or no solution. By the number of solutions, we can classify the system. So if there's a solution, that means that the graphs must collide. And if they collide, that means that the systems are consistent. So if there's one solution, we would say that graphs or the systems are consistent. If there are infinitely many solutions, they collide, so we would say that the systems are consistent. But if there is no solution, they are inconsistent because they do not collide. Now, we can further differentiate our consistent systems according to the number of times they collide. So if they collide one time, if they collide at a point, I want you to think of being independent means that you can stand all by yourself as one person. So if there's one point, we say that it is consistent and independent, the system. If there are infinite points or infinitely many points, so if your solution is either a line or a plane, then we say it's consistent still because there is a solution, but it's dependent. And so think about, like, if you're dependent, you depend on many people, and so that would correspond to many solutions. If you're independent, you depend on yourself, one person. So let's go back to the problems on the first page. So if I take a look at that first graph, this is an example of a system where I've got three planes that all intersect at one point. Because there's a point of intersection, because they collide at some point, I can say that the system is consistent. And because there is only one point of intersection, I would say that it is also independent. If I take a look at the second one, I can see that those planes collide. So therefore, they are consistent. But notice that they collide along a line. There are many points along that line. So that means that this is a consistent and dependent system. In letter C, I can see that the planes intersect, but they don't all intersect at the same place. So like these two planes intersect here, these two planes intersect there, and these two planes intersect here. But they don't all three intersect at the same spot. So they don't all three collide. So therefore, we would call this an inconsistent system. Okay. So if you're given a graph, I think it's pretty straightforward how to label the solutions or classify the systems. In letters D and E, you're actually given the systems, and you have to classify them according to the number of solutions. And the best way to do this is to just start solving. And the first step in solving is to try to eliminate one of the variables. You want to pick a variable that's going to be easy to eliminate. So for example, if I look at this first system in letter D, I'm going to try to find variables that that have a coefficient of 1 or negative 1. And so in this case, I can see that x or y are going to be the easiest variables for me to eliminate. And so I'm going to just think about what would happen if I group these two equations together and these two equations together. If I group the first two, if my goal is to eliminate x, then I would want to multiply my top equation by 2. And that way I'm going to have a negative 4x, and that'll cancel the positive 4x below it. So I'm just going to go ahead and rewrite this equation. I'm going to have a negative 4x. That's going to lead me to a positive 2y. If I distribute the 2 to the negative 12, that's going to give me a negative 24z. And then don't forget to distribute the 2 to the 9 as well. That's going to give me 18. And when I combine it with the second equation, a funny thing happens. My x's cancel, my y's cancel, and my z's cancel. When all of your variables cancel, that means you have nothing left on the left-hand side of the equations. And on the right-hand side, 18 plus 3 is 21. Well, 0 does not equal 21. This is a false statement. So as soon as I get to this point, I know that I'm not going to have a solution to the system. There is no solution to the system because that statement is false. And if there's no solution to the system, I don't really have to do any more work. It must be inconsistent. And that is where we're going with this problem, is to be able to classify the system. So it is an inconsistent system. And I don't have to do any more work. I don't have to try eliminating the x in another equation, because as soon as I get a situation where my variables fall out and I'm left with a false statement, I know it's an inconsistent system. If we take a look at letter E, I can do the same thing. In this case, I can see that my y variable is the only one that sort of has a coefficient of 1 or negative 1. So I'm going to focus on eliminating my y variable. And again, I'm going to combine my first two and my second two equations. If my goal is to eliminate y, then I'm going to need to multiply the second equation by a positive 3 so that I'll have a negative 3y canceling the positive 3y in the first equation. So I'm going to bring the first equation straight down. 6x plus 3y minus 9z is equal to 12. And if I distribute it through that 3, I'm going to get a negative 6x minus 3y plus 9z. And if I distribute it over, that's going to give me a negative 12. And if I look at this, I can see that everything cancels this time. And so I'm going to be left with 0 equals 0. Well, that means that these two equations represent the same plane. They are the same plane. So between the two of them, I'm going to have an infinite number of solutions. Let's go ahead and see what happens when I combine the second and third equations. And again, my goal would be to eliminate the y variable, which means that this time I'm going to need to multiply by a positive 6. And when I multiply through, I'm going to just do this really small next to it. 6 times negative 2 is going to give me a negative 12x. I'm going to have a negative 6y, a positive 18z. And if I distribute the 6 to the negative 4, I'm going to have a negative 24 on the other side. The second equation is positive 12x plus 6y minus 18z, and that's equal to a positive 24. And again, you can see everything cancels. And so I'm going to be left with 0 equals 0. So if the first equation and the second equation represent the same plane, and I just found out that the second equation and the third equation represent the same plane, then really this is 3 planes on top of each other. And so that means that I have a consistent system with infinitely many solutions, and so that means it's going to be consistent and dependent because there are many, many solutions. So this statement here means that there are infinitely many. It basically means that the equations are the same, so I'm dealing with the same plane. Okay. In the second problem, you're given a solution, or you're given an ordered triple, and asked if it's a solution to the system. Whoops. In order for it to be a solution to the system, the point has to work for every single equation in the system. So what I usually do, because this can get tedious, is I like to rewrite my equations and then just put parentheses where the x, the y, and the z are supposed to be. So I'm going to show you what I mean. So for my first one, it's going to be, my x minus y plus something equals 2. In the second equation, it's going to be 2 times x plus y minus z equals 0. And then in the third one, it's going to be a negative, parentheses, minus 3, parentheses, plus 2, parentheses, equals 3. And then it makes it really easy for me just to plug in all my x values, so 0, 0, 0, and then all my y values and all my z values. And I find that when I do it this way, I don't make careless mistakes, because this is a problem on your quarterly assessment that you must be able to do without a calculator. And so now I'm going to take each equation one step at a time. So if I take a look at the first one, remember with addition and subtraction, we just go in the order that they appear. So I've got 0 minus 1, that leaves me with negative 1. And if I add negative 1 plus 3, I get 2. So that's actually a true statement. If I take a look at the second equation, I've got to first do my multiplication. Following my order of operations, I'd have to do the 2 times 0, which is going to give me 0. And then I'm going to be left with 1 minus 3, which is negative 2. And negative 2 does not equal 0, so I know that that is not true. And I don't really need to go any further. As soon as I find a situation where the ordered triple doesn't work, I know that it can't possibly be a solution to the system. Just make sure that you answer the question. No, 0, 1, 3 is not a solution. Now, if it happened to work for the second equation, I would still have to test it in the third equation before concluding that it is a solution to the system. In fact, if I do that, I don't have to worry about a negative 0. That's still going to be 0. And then I have negative 3 times 1 is going to be negative 3. And this is going to be plus 2 times 3 is going to be plus 6. And so negative 3 plus 6 is 3. So it does work for the third equation, but since it doesn't work for the second equation, it can't be a solution to the system. It's got to be a common point for all 3. All right, so let's take a look at number 3. It says to consider the following system. So you're given a system with 3 variables, 3 equations, and it says to rewrite the first equation in terms of z. So one of the things you have to be able to do on the quarterly assessment is solve for different variables. And this would be the process that you would use if you were solving using the substitution method. So basically what I want to do in that first equation is get the z all by itself. So if I have 3x plus 2y minus z equals 3, if my goal is to get the z by itself, then I need to subtract the 3x. So I'm going to subtract it from both sides. I might as well go ahead and subtract the 2y while I'm at it. And that's going to eliminate the x and the y from the left-hand side. I'm still going to have a negative z on the left. And then on the right, if I can't really combine anything, so if I write it as a negative 3x minus 2y plus 3, and the order actually doesn't matter because it is addition and subtraction, so you can move things around. But I'm still not finished. That negative in front of the z is like a negative 1. And so if I want to get z by itself, I still have to divide by negative 1. And if I divide by both sides by negative 1, I ultimately have to distribute that negative 1. So z would ultimately be a positive 3x plus 2y minus 3. And then in letter B, it says to rewrite the second equation in terms of y. So now I'm going to take a look at my second equation, and the goal is to get that y by itself. So let me rewrite it. I've got 2x minus 4y plus 2z is equal to 2. And if I want to get my y by itself, I'm going to first need to move the 2x and the 2z, and I'm going to do that by subtracting. And so my x and my z will be gone from the left-hand side, and I'm going to be left with negative 4y is equal to negative 2x minus 2z plus 2. And just like I had to divide by negative 1 in the last equation, this time I'm going to divide by negative 4. And when I divide both sides by negative 4, it's the same as distributing that dividing by negative 4 to each term. And so I'm going to be left with y equals, well, negative 2 over 4 is just going to reduce to a positive 1/2, and I can write that as x over 2, or I can write it as 1/2 x. It actually doesn't matter. The same is going to happen to the coefficient of z. Negative 2 divided by negative 4 is 1/2, or z over 2. And then the last term is 2 divided by negative 4, so that's ultimately going to reduce to a negative 1/2. And that would be writing the second equation in terms of y. So it is important that you can manipulate equations and move the terms around using your inverse operations. Okay. In number 4, it says, Shania and her two friends, Lisa and Joey, go to the fair on Wednesday night. Shania buys 10 ride tickets, 6 game tickets, and 4 food tickets for $24. Lisa buys 3 game tickets, 8 ride tickets, and 2 food tickets for $15. And Joey buys 6 food tickets and 9 game tickets for only $21. If we let X represent the cost of 1 game ticket, Y represent the cost of 1 food ticket, and Z represent the cost of 1 ride ticket, we're asked to write a system of equations to represent the situation. So one of the things that you should pay attention to is the order that each of these expressions is written, because they're not written in the same order. So Shania, we're first talking about rides, and then games, and then food. But with Lisa, we're talking about games and then rides and then food. So I want to be careful about how I organize my equations. And one of the things that I think would help is, since our variables are already defined, to go ahead and mark the variable next to each of the terms. So for example, if Shania buys 10 ride tickets, a ride ticket is actually my z variable. So I'm just going to cover it up with a z. 6 game tickets means that that's going to correspond to the x variable, and food tickets correspond to y. With Lisa, she buys 3 game tickets, and so again, a game ticket corresponds to x, 8 ride tickets corresponds to z, and then 2 food tickets is going to correspond to y. And then Joey buys 6 food tickets, so that's again going to be y, and 6 game tickets, which is going to be x. And so when I go to construct my equation, I want to make sure that I do things in order. So I'm going to have Shania, and then her friend Lisa, and then Joey. And it might even help to organize. So if I have X, that's going to be the games. And then I'm going to have food for Y. And then the ride would come next. So it might actually help, and then the total would be over here, to kind of lay things out this way. So for Shania, I know she had 10 ride tickets, so that's going to be 10Z. And then I know she had 6 game tickets, so that's going to be 6X. I know she had 4 food tickets, so that's going to be 4Y. And I know I'm adding everything together, and I know she spent a total of $24. And so that helps me set up the equation. When I'm thinking about Lisa, she buys 3 game tickets, so that's going to be 3X. 8 ride tickets, that's Z, so 8Z. And 2 food tickets, that's Y. And again, she's adding all of those things up, and it says that she spent $15. And lastly, Joey buys 6 food tickets, so that's 6Y. And 9 game tickets, so that's going to be 9X. And I know that Joey spent a total of $21. And there are your 3 equations. So just pay attention to the order that the expressions are written, If it helps to define your variable, like if the variable definitions aren't given, sometimes it helps to call like the game tickets G, the food tickets F, and then the ride tickets R when you're putting them in the equation, and then just kind of organizing them from there. But I do think it helps to kind of organize the columns using headings of the items that are being purchased. Okay, you were not asked to solve this equation, just set it up. Okay. In number 5, it says, while at the movies, Mr. Johnson purchased 2 large tubs of popcorn, 4 drinks, and 1 box of candy for $31. Mrs. Spiegel purchased 1 large tub of popcorn, 2 drinks, and 2 boxes of candy for $20. And Jake, a friend of both families, purchased a drink and a box of candy for $7. Very similar to the last problem we had, you're asked to determine the cost each of a large tub of popcorn, 1 drink, and a box of candy. So let's sort of set things up. So I'm going to have Mr. Johnson, I'll just call him Mr. J, and then we know that he purchased popcorn. And let's go ahead and define our variables here. So if we have cost of popcorn, let's call that X. And then my drinks, so let's call that Y, the cost of a drink. And then the candy we'll call Z. And make sure you're specific about whether it's the number of drinks or the cost of the drinks. And in this case, it's very clear that we're looking at the cost of each of these items. And then we're going to have a total over here. So if I'm thinking about Mr. Johnson, he purchased 2 large tubs of popcorn. Actually, let me go ahead and list everybody else. So I've got Mr. Johnson, Mrs. Spiegel, and then Jake. Okay, so let's go ahead and take a look at Mr. Johnson. He purchased 2 large tubs of popcorn, so that's going to be 2X, 4 drinks, so that's going to be 4Y, and 1 box of candy, so that's just going to be a plus Z. I'm not going to bother putting the 1 in front, and he spent $31. Miss Spiegel purchased 1 large tub of popcorn, so again, I'm not going to put the 1 in front, 2 drinks, and 2 boxes of candy, and she spent $20. And then finally, Jake, a friend of both families, purchased a drink, so 1 drink, so that's just going to be Y, and a box of candy, which is going to be Z, and he only spent $7. Okay, so here's our system. It's set up. I've defined my variables. That's very important that you do that. The next step is to solve it, because if I'm trying to find the cost of each of those items, I have to actually solve the system. The one thing I notice is that I have an equation where Y and Z are all by themselves and I don't have an X. So if I could combine the first 2 equations and eliminate my X variable, I'll have another equation with just a Y and a Z in it that I can combine with my 3rd equation. So that's my goal. I'm going to combine the first 2 equations and eliminate X so that I wind up with an equation that I can combine with the 3rd one. So in order to eliminate the X, I'm going to want to multiply this 2nd equation by -2. And so I'm going to do my work below my system. I don't want to like contaminate my system that I set up because it'll make it a little bit hard for your teacher to grade. So I'm going to rewrite down at the bottom. So I'm going to keep the first equation the same. 2x plus 4y plus z is equal to 31. And then in the second equation, I'm going to multiply everything through by -2. So I'm going to have a -2x. This is going to give me a -4y and a -4z. And if I multiply -2 times 20, I'm going to get a -40. And what's nice about this is my x's cancel, and so do my y's. And so what I'm left with is a -3z is equal to -9. And this is awesome because if I divide both sides by -3, I get that z is a +3. And that is sweet because I've already solved for one of my variables. And so all I need to do now is take that solution and plug it into that last equation. So if I know that y plus z is 7, and I know that z is 3, whoops, then I can really easily solve for y. If I subtract 3 from both sides, I find that y is equal to 4. And if I know z and I know y, then I can very easily plug both of those numbers into either of the first 2 equations to solve for x. I'm going to go ahead and just do it in the first one. So we have 2x plus 4y. So it's going to be 4 times my solution, which is 4. And then I've got plus z, or plus 3, and that's got to equal 31. So when I simplify, 4 times 4 is 16, and if I add that to 3, I get 19. So we have 2x plus 19 is equal to 31. And so to solve, I'm going to subtract 19 from both sides. Cancel out, and I get 2x is equal to, well, 31 minus 19 if I'm not even going to use my calculator. So if I borrow from the 3, I've got 11 minus 9, that's going to give me 2, and then 2 minus 1 is going to give me 12. So I get that 2x is equal to 12. If I divide both sides by 2, I get that x is equal to 6. Now the last thing that's very, very important is that you put your answer in the context of the problem. Remember, we're talking about the cost of popcorn, drinks, and candy. And so I want to go ahead and write my answer. So popcorn costs how much? That's my x variable. So popcorn costs $6. My y variable corresponded to the cost of a drink, and z to the cost of candy. So drinks cost the value of y, which is $4. And box of candy, or one box of candy, costs, and that's the value of z, which is $3. And so now you've finished solving. Okay, so that wraps up the review of our first unit. You can check back or look for the review for quadratic functions, which is going to be my next video. And then after that, there'll be a video on polynomial functions as well. Good luck.